solve this recurrence relation. Yeah. And let's look at it from the problem solving point of view. Yeah. All right. Yeah. I just talked about the shift operation faster than addition. Yeah. That background slightly. Yeah. All right. So here we treat plus this addition plus 1 as the basic operation. Okay? Yeah. So let's count the number of basic operations. And we use this A function representing the number of additions we need to find the answer. A function, capital A function, as the number of additions. Yeah. Then, based on our recurrence relation, we have a slight, almost the same form of the original, yeah, because the number of additions for the problem size n equals the number of additions for the problem size floor function of n over 2, then plus 1 more. Yeah. And number of addition, let's just treat 1 when n equals 1, although you may feel no addition, but here let's just treat as 0 plus 1 as 1 addition. Okay? Yeah. Yeah. In that way, so you can see these two recurrence relation basically the same. Yeah. So here we just solve the same recurrence relation. Yeah. All right. How to solve it? Yeah. And here, if you look at the main part of the equation, yeah, which part is the hardest to process? Yeah. Here we treat data processing work. So the hardest part to work, yeah, which part you feel it is the hardest to do the work, to do the processing work? Yeah. Look at this part. Do you feel the floor function part, could cause some processing difficulty there? The floor function. Do you feel handling the floor function in this recurrence relation make you feel a little hard? Yeah. Yeah, usually it is. Yeah. The floor function makes working on this equation harder. Yeah. So the next question is how to make it simpler. How to make it simpler. So we want to make our equation as simple as possible. How to make it simpler? Yeah. All right. Let's consider special cases. To make this simpler, let's consider some special cases. Can you see some special case that we can make the original equation simpler? Special case make original simpler? Yeah. Yeah. All right. Yeah. So now we are looking at the floor function part. Yeah. All right. All right. So here, when you look at the floor function part, when n is an even number, you can remove that floor function to get n over 2. For n is an even number, you don't need that floor function symbol. You just get n over 2. Yeah. But for n is an odd function, you can still remove the floor function notation and you get a parenthesis n minus 1 over 2. Yeah, both. So you can, in these both cases, you can remove that floor function. Yeah. So we don't want to see the floor function in our equation. That makes the equation hard. Yeah. Hard. Yeah. All right. So now, yeah, because usually when we work on a relatively hard problem, we want to consider some simpler cases. Yeah. Okay? Yeah. When we start, we want to work on simpler cases. Yeah. So here, we have two cases, n even and n odd. Which one you feel simpler? The even case simpler or odd case simpler? If you need to solve this problem, do you like work on the even case or you like work on the odd case? Yeah. Which one you feel easier? Yeah. Any of you have an idea? Yeah. So you can see, yeah, even case simpler, right? Even case looks simpler. So if even case simpler, let us just assume we are working on even case. N is even. Let's assume n even first. Okay? If n is even, then we can simplify this equation, right? Yeah. So we can simplify it by removing the floor function. But after that, you need to do another recursive function call, and the second time when you apply this equation on the smaller problem size, this time you need to do n over 4 floor function. N over 4 floor function. So you get a floor function again the second time. And that still make the equation harder. Yeah. Yeah. So in order to make the second step simpler, you may like to assume n is multiple of 4. Yeah. Or n over 2 is even. So n is multiple of 4. N over 2 is even. Yeah. And so on. Yeah. But how to make the whole thing simpler? Yeah. So you do the recursion again and again from beginning to end, and you do not need to worry about the floor function. Only when n is a power of 2, you can remove all the floor functions, right? Yeah. So if n is a power of 2, then all the floor functions are gone when you do recursions. When you do all the related recursions, floor function gone. Okay? So with that observation, let us assume we just take our first simplest case. We take n is a power of 2. Yeah. Because we don't want to deal with the floor functions. So n is power of 2, all floor functions disappear. Yeah. All right. So k, we can represent it as a log base 2 of n. K. Yeah. The relationship between k and n. Yeah. All right. So now let's write our new recurrence relation, but this time we can use n equals 2 to the k. Yeah. All right. So in this new recurrence relation, yeah, how to solve this new recurrence relation? Yeah. Yeah. Let's do the work. Okay. All right. The first time, this is our first equation. Yeah. The second time, we do division by 2, so we reduce the problem size, division by 2. Yeah. Next time, another division by 2, yeah, but we always get the problem size power of 2, yeah, and so on, dot, dot, dot. And the last one, so this is the last one. The bottom, when we reach the bottom, we get the last equation, like this. All right. Then, let's add up all these equations together, both sides. Can we do cancellation? Left-hand side term, right-hand side term, if they are the same, we can do cancellation. Okay? Yeah. So let's do all the possible cancellations in this diagonal way. Yeah. At the end, what do we get? At the end, the left-hand side, only one term left. A of 2 to the k left. The right-hand side, this many ones. Yeah. How many ones? We need to count how many equations do we have. And then capital A of 1, and this number, by the initial condition, it is 1. Okay? All right. But we want to count the number of ones. Yeah. How many equations do we have? Yeah. If we know the number of equations, then we know the number of ones other than this A of 1. Yeah. Can you tell me how many equations we have here? Counting, still remember counting by reference? Counting by reference, can you find suitable reference objects? Good. Be careful a little bit, Eldon. Be careful a little bit. Look at your reference. So you're close, but be careful. There is one small problem in your answer. K, yes, not N. It's K. Yeah. So then the final answer, A of 2 to the k equals k plus 1. And the k, we have the representation log base 2 of n. Yeah, so we can write our result. A of n equals 1 plus log base 2 of n. That's the final answer. Yeah, final answer. All right, so see? Yeah. All right, so we have the final mathematical formula for the solution to get the number of bits, yeah, the number of bits for integer n. Yeah. But we need to go back to our assumption, because we only have this result when n is power of 2. Yeah. If n is not power of 2, can we use this formula? If n is not power of 2, can we still use this formula? Yeah. No. Yeah. Because if n is not power of 2, look at this term. Log base 2 of n won't be an integer. If you still use this formula, when you plug in that n integer into this log function, log base 2 of n, it won't be an integer. That's not right, right? Because your number of bits should be an integer. Number of bits must be an integer, but this function does not return an integer for you. How to fix it? How to when n is not power of 2, how to fix it? Yeah. Because we want to get an integer. How to fix it? Okay? Yeah. Do you have any idea? Yeah. So here we need to solve another technical problem. Yeah. The given formula is a non-integer representation, but we want to have an integer representation. So the question is, how do you, and we know this representation, although it's not an integer representation, but it is very close to our final answer, right? It is a very close one. Okay? So the way to fix it, we want to find another integer representation that is close to this formula. That's what I want to say. Yeah. How to convert this non-integer representation to an integer representation, but these two formulas should be very close. Do you have any simple way to do the conversion? Think about that. Okay? Think about that. What's the simplest way you can convert an integer function, a non-integer function, to an integer function? The simplest way. Okay? Yeah. Two possible ways. Floor function and the ceiling function. Think about that. Floor function and ceiling function. Yeah. All right. Yeah. Because very close, right? Floor function of some representation is very close to the original representation. Yeah. Very close. Ceiling function also, yeah, it's an integer representation and very close to the original representation, right? So here, here, when we make a guess, so here we want to make a guess. When we make a guess, there are two possible versions we can use in our guess. Okay? One use floor function, another use ceiling function. Yeah. Both ways we can get an integer representation. Yeah. So the next question, which one is correct? Because these two representations are different. Only one could be correct. You cannot have two correct formulas. Okay? So the question, which one is correct? Or which one is incorrect? So we can throw it away. Incorrect. Do you have any idea to tell? Yeah. How to find the odd one? How to find the odd one? Have any idea? Simple way to eliminate the wrong one. Any idea? The strategy we used before. Okay? I mentioned some simple, effective strategy we used before. Yeah. Do experiments. Do experiments for simple n numbers. Yeah. Here, so let's do example. Let's consider for n equals 3. Do experiment. Okay? Yeah. Let's plug in n equals 3 and see which formula gives us the correct answer. Now, first, 3, the binary representation is 1, 1, right? So n, if we use the binary representation, it's 1, 1. Okay? How many digits? 2 digits, right? So a of 3 equals 2. Okay? All right. Then, if we consider these two functions, one is 1 plus floor function of log base 2 of 3. The second is 1 plus seeding function of, oh, sorry, another computer run out of battery. Let me just connect it. Yeah. So log base 2 of 3. Look at that. Seeding function to 1 point something. You get 3, right? So here, floor function 1, you get 2. See? The floor function, you get the same number 2. The seeding function, you get a different number. Yeah. Based on this observation, you can see which one is correct. The floor function is correct, right? Yeah, the floor function. So this is a simple way to, when we have more than one guesses. Yeah. Here we have 2 reasonable guesses. Okay, these 2, the 2 of our best guesses. Yeah. But we need to find the final best one. Yeah. So the floor function version is the final best one. Yeah. All right. Yeah. Okay. So here, just a simple strategy. In this class, you can see we apply a few times. Yeah. We just do experiments using simple data. Yeah. All right. Yeah. So we finish this topic. Yeah. Then let's move to the next topic, B.2, variable size reduction. Also variable size reduction, but different from B.1 variable size reduction. B.1, half size reduction. Every time we reduce the problem size by half, but this one, really the variable size. Okay? It's hard to predict how much the problem size could be reduced each time. Yeah. It depends. Sometimes more, sometimes less. Yeah. All right. So let's look at another well-known problem. Yeah. Number 9, greatest common divisor problem. Yeah. So everybody here, I think you're familiar with this problem. Yeah. But here, let's use the recursive thinking to understand this problem. Yeah. All right. Given 2 non-negative integers, m and n, not both 0. Yeah. One of the 2 could be 0, but not both 0. Yeah. The goal, find their greatest common divisor, and we use this GCD function, GCD of these 2 integers, yeah. M and integer, but not both 0. Yeah. Yeah. So that's the problem. Yeah. All right. Yeah. So here, yeah, to understand the problem, yeah. Yeah. First, why not both 0, right? So you may want to ask why not. The reason is simple, because if both 0, then the function is not defined. Okay? The function is not defined. That means GCD of 0, 0 is not defined. Can you see that? Why it is not defined? Yeah. Yeah. So you cannot choose any number for it. Yeah. It's impossible to make it equal to any integer if you look at GCD 0, 0. Definitely you cannot say it's 0. It's not 0. Okay? It's not a 0. Yeah. 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 So think about it. Yeah. So You cannot choose any integer as the answer of this function. That's the reason it is not defined. Okay? Yeah. All right. Yeah. So here, yeah. So my another computer. Yeah. So the power problem. So I run out of power. Yeah. All right. Okay. Yeah. Still, yeah. Chat. Yeah. All right. Yeah. So now let's look at the solution. Yeah. For the solution, I want to use two different methods to calculate this GCD function. The first one, the middle school procedure. Yeah. So I think you're familiar with this middle school procedure. Okay. Yeah. So let's quickly go through the details of this middle school procedure. Yeah. All right. Step 1. We find the prime factorization of n. Prime factorization. Yeah. Okay. All right. Step 2, find the prime factorization of n. Yeah. Then step 3, find all the common prime factors. Yeah. Yeah. After step 1 and 2, so you can find all the common prime factors. Yeah. Step 4, compute the product of all the common prime factors to get the answer. And here you can see this method relies on the prime factorization. Yeah. So let me use a simple example to show how it works for this example. Yeah. Let's calculate GCD of 60 and 24. Yeah. Let's do prime factorization on 60 first. We get 2 squared times 3 times 5. 2 is a prime, 3 prime, and 5 also prime. Yeah. And for 2, it has a power of 2. Yeah. 2 squared. Yeah. For 24 equals 2 cubed times 3. Yeah. Now, let's try to calculate the common prime factors. Yeah. For 2, the largest power of 2 as a common factor of these two numbers, that's 2 squared. For 3, just 3. And for 5, yeah, for 3, we need to put a 3 here. Yeah, sorry. And the product, 2 squared times 3, 12. So the answer is 12. Yeah. So this is the middle school method. Yeah. All right. So now the question. Now the question. We want to answer this question. Yeah. Is it good method? Yeah. Yeah. Is it a good method? Okay. Yeah. It looks simple, right? It looks so simple. Yeah. If it's a simple one, it should be a good one. Yeah. Yeah. But, so you really need to think more here, because this method relies on prime factorization. So then there is a question. How hard is the prime factorization? How hard is it? How hard is it? Prime factorization. And when n is large, the question. Here, our n, our integer to be factorized relatively small, 60 and 24. Very small. But think about if you have a huge integer. How big is the integer you want to do prime factorization? Think about you have an integer as big as 1,000 digit integer. If that n is a 1,000 digit integer, if you need to do prime factorization on a 1,000 digit integer, how hard it is? How hard it is? The answer is extremely hard. If you use computer to do it, even if you use a powerful computer to do it, it is still extremely slow. Extremely slow. How slow it is? Remember in our polynomial evaluation problem, we did comparison between the brute force method and Horner's rule method. And in one experiment, I show you when n equals 1 million, right? When n equals 1 million. So then the brute force method needs 5.8 days. The Horner's rule method only needs 1 second. That big difference. So 5.8 days to calculate that polynomial with 1 million degree. Yeah. But that's in days. And in this one here, 1,000 digit integer, you cannot get the answer in a certain number of days. Even number of months, still not enough. You may need a number of years to get a prime factorization. So you can imagine how slow it is. Number of years to get the answer. That's slow. Yeah. Or if not years, at least number of months. Yeah. So much slower than our brute force method to calculate polynomials. Yeah. Yeah. So and here, in order to solve this GCD problem, we want to solve this problem for large data sizes. Not small data sizes, for large data sizes. That means this middle school method won't work. Yeah. So we have to find a much better algorithm to find a solution. Yeah. All right. So that's the reason we want to consider the second algorithm. Yeah. The goal, we want to find efficient solution when our input numbers m and n extremely large. Think about that. Okay? All right. Reduce the problem size. Yeah. Yeah. So here, to find a solution, we want to reduce the problem size. Yeah. But the question is, how to reduce the problem size? Yeah. And when you reduce the problem size, you need some tool. You need some tool to do it. And here we need some mathematical tool to help us reduce the problem size. Yep. All right. So what's the tool? Yeah. So let me give you the tool first. It's called a division algorithm. It's a simple tool. Everybody knows it. Division. You're familiar with the division. Yeah. But here we call it division algorithm. Yeah. Basically, it's an integer division. Yeah. But we represent integer division in a special way, And we can use this special way to help us reduce the problem size. Yeah. So let's look at the details of this division algorithm. Given positive integers a and b with b not equal to 0, because we want to use b as the divisor. Divisor can never be 0. So we assume b not equal to 0. There exists unique integers q and r, q for quotient, r for remainder, with r between r greater or equal to 0 and strictly less than b. Remainder should be strictly less than the divisor. Yeah. Otherwise, we can change the quotient and reduce that remainder. Yeah. So we can assume the remainder must be strictly less than the divisor, such that a equals bq plus r. B divisor times the quotient number plus the remainder. That's simple, right? So that's our basic understanding when we were in the elementary school, right? Yeah. So that simple integer division method, here we make it division algorithm so we can use it as a problem size reduction tool, and it's a powerful tool here. Okay? Yeah. So here, next step, we will use this algorithm, division algorithm, to reduce the problem size. Yeah. So let's look at the work to do. Yeah. So A, B, so we replace by M and N. Yeah. All right. So when we do the size reduction, let's just assume M greater or equal to N. Yeah. If not, we just swap these two numbers. Yeah. So we can make the first parameter M greater or equal to the second parameter N. Yeah. Otherwise, we swap. Yeah. All right. And now, based on the integer division, we have M equals N times Q plus R. Yeah. All right. With this representation, now we can do the size reduction. When we apply the GCD function, size reduction in the GCD function. Yeah. Yeah. So let's look at the reduction details. Yeah. Now we consider GCD of M and N. Yeah. And we can replace M representation by NQ plus R. Yeah. All right, NQ plus R. So now you have this NQ term, NQ, that's the Q multiple of N. Here, can you do some reduction operation related to that NQ term? Yeah. So let's look at the, another different representation. Here, let's look at the M over N, this fraction first. M over N first. Yeah. So based on the M representation, so we have the quotient, that's an integer, plus a smaller fraction, R over N, right? Yeah. So the, mixed form of the fraction. Yeah, mixed form. The integer part and the fractional part, the mixed form fraction. Yeah. All right. Now, with this new representation, when we look at the common divisor of M and N, the common divisor of mn has nothing to do with the q term, right? The q is the integer part. It has nothing to do with the q part. The common divisor m and n has a close relationship with the common divisor of r and n, right? Yeah, r and n. Yeah. So, or you can say it should be also a common divisor between r and n. Okay? Yeah. So then the greatest common divisor of m and n should also be the greatest common divisor of r and n. Yeah. Yeah. Yeah, because q does not change anything related to the common divisor. So you can ignore it. When you look at the common divisor, you can ignore the q term. Yeah. So for that reason, we can simplify the original GCD expression by, basically we just eliminate n and the q, but we know r is smaller than n, so we swap m and n, r and n. We swap r and n, so we write n as the first parameter, r as the second parameter. In this way, you can see the problem size is reduced. Yeah. But this is just a one-step reduction. Can we do further reductions? Yeah. So we can apply another round problem size reduction on n and r by taking another integer division algorithm representation. So another round reduction, and keep doing the reduction again and again until at some point we have to stop. Yeah, because you cannot do it forever, right? So at some point you can stop. Yeah. Yeah, think about, at some point n equals certain multiple of r times, let's say, d. Yeah. If at some point n equals r times d, so then GCD of n and r, n is rd, r, you just take r out, GCD of d and 1 inside, but GCD this 1, common divisor of 1, only 1, right? Yeah, so that is 1. GCD of d comma 1, that must be 1. So you get r directly. So you can stop. That means if n is a multiple of r, you can get an answer immediately. As soon as you detect the first parameter is a multiple of the second parameter, you have the answer. The answer is the second parameter. So you get a final answer. You can stop. Yeah. So that's this second algorithm. The second algorithm, you can see you only need to apply integer division. You do not do prime factorization. You do integer division. Okay? So you can see the difference between these two methods. Yeah. All right. Yeah. So next. Yeah. So here we have the idea of the whole algorithm, right? Yeah. So next, I want to wrap it up with the whole algorithm. Yeah. It's called Euclid's algorithm. Yeah. Some of you may have heard of it. Okay. Yeah. Euclid's algorithm. Yeah. So very old, more than 2,000 years old, Euclid's algorithm to find the GCD function. Yeah. The rule is this. Yeah. When we write the code, it's very simple. The rule is this. Yeah. GCD of x and y, two variables, x and y, first, so definitely we want to make sure not both 0, right? So if you detect both x and y 0, you should return some error message because it's not defined. The function value is not defined. Okay? Other than that, yeah, not both 0, then you have these three cases. Yeah. If the second parameter 0, then you just return x as the function value. Okay? Yeah. So then, if x mod y, this percentage sign is the mod operator. If x mod y equals 0, that means x is an integer multiple of y, then you just return the y value. The second case. Okay? All right. Then the third case, you do size reduction. Okay? So you make the second parameter y as the first parameter, and then you take the remainder, x mod y, that's the remainder of the division, yeah, x by y, yeah, as the second parameter, the size reduction. Okay? Yeah. Yeah. But when this is a recursive function call, so when you calculate this value, you apply these three cases another round. Okay? Yeah. So keep doing reduction. Yeah. And at the end, you get the answer. You get the answer. Okay? Yeah. Yeah. So that's the Euclid's algorithm. Yeah. Very simple, but if you calculate GCD, this one is very fast. This one is very fast, comparing with prime factorization method. Okay, prime factorization method. Okay, all right, and this one, because right now you are working on your programming project number 1, and this one I may like you to do a programming project number 2 using this one. Okay, so you calculate GCD in 2 different methods. The first one, prime factorization method, and the second one, Euclid's algorithm. Then you compare how big is the difference. Yeah. This one as your second programming project. Okay, yeah. So I will write the project description, and at some point, yeah. So before the deadline of the first one, I need to assign the second one. Yeah. Otherwise, we won't have enough time to work on the second one. Yeah. So try your best to work on the first one. Yeah. Yeah. So I post a discussion board for project 1 questions. Yeah. So if you have questions, you can post in that discussion board. Yeah. All right. So let me see. Yeah, I have 10 minutes left. Yeah. So I can talk about one thing related to the prime factorization. Yeah. Yeah. So using this 10 minutes, some background information. Background information about prime factorization. Okay. Yeah. And here, as I told you before, the prime factorization is extremely slow. Yeah, so yeah, because even take number of months or years, that's slow. So slow. Okay? Yeah. So for thousands of digits, that large number. Okay? Yeah. So slow. The question is, yeah. And based on our impression, so we know slow is a bad thing, right? Yeah. To do prime factorization in such a slow way, it's a bad thing, very bad. Yeah. But there is an interesting question to ask here. Yeah. Is there some special situation in which we can make that slow computation a good thing, not a bad thing? A good thing, so that means we can use this property to do some useful work. Not some bad thing. We can use this property. So what property? Slow computation property. This prime factorization is extremely slow. This property can be used to something to our benefit. To our benefit. That kind of thing. Do you know, is there any situation like that? Yeah. Slow is good. Slow computation is good, not bad. Is there any situation like that? Yeah. Yeah, let me know. So here, yeah, let me tell you, there is one special situation. Okay? Yeah. Encryption situation. Yeah. Think about encryption problem. Yeah. Here we are looking at the encryption problem. Okay? So yeah. In our internet era, we know the information security is very important. When we send some important data, we want to protect our data, right? So we want to do encryption on our data, so that the hackers to make it very hard to break for the hackers. Okay? So here, the slow computation here, we want to make the hackers breaking work as slow as possible. Think about that. Yeah. We want to make the computation from the hackers as slow as possible. That's the idea. Okay? For us, we want to get our computation result as fast as possible. But in order to protect our valuable information, we want to make the breaking time as long as possible by the hackers. Think about that encryption problem. Okay? Yeah. So based on this idea, two mathematicians as I remember, MIT, two mathematicians, they designed a very powerful encryption algorithm using this property. Prime factorization very slow using this property. They designed an algorithm called RSA algorithm. That's the initials of these three professors. RSA encryption algorithm. Okay? Yeah. So they use the prime factorization of large, very large integer. Okay, very large, huge integer. Okay, thousands of digits, huge integer. Yeah. Yeah. All right. So let me see how long, how many minutes do I? Yeah, I have 4 minutes. Yeah. So let me quickly talk about that idea. Yeah. All right. Yeah, because so here assume a given integer. So there is integer. Yeah, let's say n equals p times q. These two both, yeah, both pq, they're both large primes. Prime. Yeah. So you do multiplication on 2,000 digit primes, that large, 1,000 digit prime. So you get a very large number n. Okay, n. And here, you know, when you make that n, you just do multiplication on 1,000 digit primes. It is still very fast, right? Multiplication on 2,000 digit primes, still very fast, extremely fast. But when you go the opposite way, when you are given n, you need to do prime factorization to find the p and the q, extremely slow. The opposite way, the prime factorization, extremely slow. How slow? In months or years, that level. In number of months or years. Okay, all right. Then, this RSA algorithm is designed based on this large number. Okay, so this large number can be sent to the users as a public key. So we know public key. Okay, for coding encoding, so usually the user, they need a pair of keys, public key and a private key. Yeah. Public key, so you can send, you know, broadcast. Everyone can get that. Public key. The private key, you know, so it should be delivered in a secret way. Secret way, you know, the code book, you know, secret way. Yeah. So that in the, you know, encryption, yeah, field. Yeah. So then the user, after they receive the public key, because the private key they maintain, yeah, they need to maintain the private keys, you know, in some special way. Yeah. But after they receive the public key, yeah, they apply, yeah, because they have the private key, so they can apply on the public key, they can find the prime factorization quickly. Quickly, okay? Yeah. But the hackers, they only have the public key, they don't have the private key. So they cannot apply the fast algorithm, RSA fast algorithm to find a P and a Q. They have to do the prime factorization to get a P and a Q. That's extremely slow. So, yeah. So in that way, so this method can protect valuable information. Yeah. All right. So that's the, you know, the background, yeah, for this topic. Yeah. All right. So let me stop right here. Yeah. So we finish part B. Yeah. So next we have part C and D for this module. So another class we will finish module 3. But now we are ready for our first big assignment, homework assignment number 1. Yeah. So I will post sometime tomorrow our first big assignment, preparing you for the midterm. Yeah. Midterm.